Imagine you're sitting down to take a math test.
Okay.
You've got your pencil ready, you flip open the booklet, and the very first question on the page is what is 2 plus 2?
You write down 4 almost instantly.
Exactly. It requires practically zero brain power, right? You don't even have to pause. But you flip to the next page, and the question is a brutally complex multi-step calculus problem.
Which is a totally different story.
Right. You are going to stop, squint, grab a piece of scratch paper, and really chew on that problem for a few minutes. I mean, you certainly wouldn't spend the same massive amount of mental energy on the simple addition problem as you did on the calculus problem. That would be absurd.
Completely inefficient.
Yet, believe it or not, when you use modern artificial intelligence today, that is exactly what is happening under the hood.
Yeah, it's a profound, almost hidden inefficiency in how these massive systems are built. The large language models that you and I interact with every day have what we call a rigid static depth.
Static depth.
Right. So whether you ask them to write a highly intricate Python script to parse a database, or you literally just type the word hello, they fire up their entire massive neural architecture. They run your prompt through every single layer of their digital brain.
Treating the simple greeting with the exact same computational weight as the complex coding problem.
Exactly.
Which brings us to the focus of today's deep dive. We're looking at a fascinating state-of-the-art research paper that just might change how all of this works. It is titled Dr.LLM, Dynamic Layer Routing in LLMs, and it's authored by Ahmed Hikal and a brilliant team of researchers.
It's a really significant piece of work. The mission for our deep dive today is to really pull apart this breakthrough method, because these researchers have essentially figured out a way to teach rigid AI models how to dynamically adjust their thinking depth on the fly.
And the incredible part, the part that really caught my eye, is that they're doing this in a way that saves immense computational power.
While actually improving the model's logic and math skills at the same time.
Okay, let's unpack this. Because to really appreciate what Dr.LLM is doing, we have to understand the problem it's trying to solve. You mentioned the static depth problem earlier.
Right.
If you are listening to this and wondering how an AI actually thinks, it's essentially a giant stack of transformer layers.
Like an assembly line.
An assembly line, exactly. Right now, the standard procedure is to push every single word or token all the way down that assembly line through every single layer. That seems like a massive waste of computer power for the easy questions.
It is a massive waste. But, the flip side is just as problematic. It is also surprisingly inflexible for the hard reasoning tasks.
How so?
Well, sometimes for a really complex logic puzzle, the AI might actually need more depth than the assembly line provides. The AI community has known this is an issue for years.
So why hasn't it been fixed before this paper? I have to imagine people have tried.
Oh, they absolutely have. But past attempts usually came with fatal flaws. For instance, some researchers tried things like early exits or layer pruning.
Early X's.
Yeah, the idea there was simple. Let the model just stop thinking early and exit the assembly line if it feels confident it has the answer.
That sounds logical. Why didn't that work?
Because it often traded accuracy for speed. You ended up with a model that was certainly faster, but it made significantly more mistakes. It would get overconfident on a tricky question, exit early, and give you the wrong answer.
I saw in the background research for this deep dive that they also tried things with very sci-fi sounding names like looped architectures or mixture of experts.
Yes.
But reading between the lines, those seem like a nightmare to actually build.
They really are. Methods like mixture of experts demand massive structural changes to the AI. You have to essentially rip the brain apart and rebuild it from scratch.
Wow.
And that means you have to retrain the model on colossal data sets, which costs millions upon millions of dollars in computing power. There was also another method called COLA, which tried to route layers dynamically, but it relied on a super expensive search process, while the model was actually generating the answer for you.
Live as you're typing.
Right, during inference, as we say. It was doing so much math just to figure out how to answer you that it was too heavy to be practical for real-world use.
Enter the Dr.LLM solution. Dr.LLM stands for Dynamic Routing of Layers for Large Language Models. And the brilliance here is that instead of rebuilding the AI from scratch, this framework just retrofits a frozen, already trained LLM.
Frozen being the key word there.
It's like taking a car you already own and just bolting on a turbocharger. They attach these tiny, lightweight routers at each layer of the model's brain.
Exactly. They do not touch the billions of base weights, the fundamental parameters that make up the AI's core knowledge. They just add these tiny traffic cops, the routers, at every layer.
Okay.
And for every single layer in that assembly line, this router looks at the information coming in and makes one of three very distinct choices.
So if these routers act like traffic cocks, what kind of directions are they actually giving? Because if the AI usually just drives straight down the highway, these routers have to be doing something radically different.
We have three main options. The first choice is to skip.
Skip.
Just bypass the layer entirely. Send the data straight to the next stop. The second choice is execute. So default, just run the layer normally, exactly like the base model would have done anyway.
Right.
And the third choice, which is the really novel one, is repeat.
Wait, repeat. As in, run the exact same layer twice in a row.
Yes. Run the exact same layer twice in succession before moving on.
That feels like the scratch pad analogy we talked about earlier. If I'm doing a calculus problem, I don't just read the equation and immediately write the answer. I loop over the numbers in my head a few times. I refine my thought process.
You're allocating more mental resources.
Right, so that third choice gives the AI the ability to allocate extra computational power specifically to the moments where it's struggling.
That is a perfect way to visualize it. But if we connect this to the bigger picture, it introduces a monumental challenge. How do you actually train an AI to make those skip, execute, or repeat decisions?
Right, because if you are listening to this, you might be thinking, oh, if the AI skips the wrong layer, doesn't it just break its train of thought? Doesn't it just get dumber?
It absolutely would. If the router makes a bad call, the final answer will be garbage. That is where the secret sauce of this paper comes in. To train these routers, the researchers used something called offline Monte Carlo tree search, or MCTS.
Okay, I need an ELI 5. Explain it like I'm 5 for Monte Carlo tree search, because that sounds incredibly intimidating.
It's a mouthful, for sure. Think of MCTS like a chess computer. When a chess computer is deciding on a move, it plays out thousands of potential future games in its head.
Oh, like if I move my knight here, the opponent does this, then I do this.
Exactly. It explores all the branching paths to find the sequence of moves that leads to a checkmate. The researchers did exactly that, but instead of chess moves, the algorithm was exploring thousands of different pathways through the AI's layers. Skip, execute, skip, repeat. Trying to find the perfect path to the right answer.
And the word offline is doing a lot of heavy lifting there, right? Because earlier we talked about how doing this live, while the AI is typing out an answer to you, is way too slow.
That's the crucial distinction. They did all this exploring before you ever interact with the model. They gave the AI complex logic questions from a famous dataset called ARC and difficult math questions from a dataset called DART. Then, they let the MCTS algorithm loose to explore all those branching paths offline.
But they didn't just let it wander aimlessly. They gave the search algorithm some incredibly strict ground rules, essentially a tight compute budget.
Right, because it couldn't just choose to repeat every single layer forever to get the right answer. That would defeat the purpose of saving energy.
Exactly. The path length was capped at what they called 2L, meaning the AI could never take more than twice the original number of layers. It was only allowed to skip a maximum of 2 layers in a row, and it could only repeat a specific block once. They forced it to find a path that was not just accurate, but highly efficient.
And importantly, the MCTS was instructed that it could only save a pathway if that pathway either perfectly maintained the model's original accuracy or actively improved it while staying under that strict budget.
So no step backwards.
None. It was essentially mining for gold, finding the rare, perfect, most efficient routes through the AI's brain for different types of reasoning problems.
I think the craziest part of this entire paper is the sheer efficiency of that training process. When you read about AI these days, it's always, oh, train on 3 trillion tokens, or took 6 months on a supercomputer.
Right.
But here, the MCTS discovered just 4,000 of these perfect ground truth paths. That is a tiny, incredibly cheap data set.
It is remarkably small because they only had to train these tiny new routers using those 4,000 paths, and they completely ignored the billions of parameters in the base model. The entire training process took just 4 hours.
4 hours.
And it was done on a single 40-gigabyte NVIDIA A100 GPU.
On one GPU. If you are listening and you aren't deep into the AI hardware space, a single A100 is something a university lab or a small startup could rent for a few bucks an hour. They did this before lunch. That is staggering.
What's fascinating here is the clever engineering of the routers themselves. Because to build something that trains in 4 hours, and more importantly, doesn't slow down the AI when you're actually using it, the architecture has to be incredibly lean.
Yeah, if the router takes longer to decide whether to skip a layer than it would take to just run the layer in the first place, you have completely defeated the whole purpose. So how did they build them?
The researchers built these routers as lightweight MLPs, multi-layer perceptrons. Specifically, they're tiny two-layer linear models structured as linear GELU linear.
Okay, stop right there. Linear, GELU linear, and multi-layer perceptrons. Translate that into plain English for us.
Okay, imagine a funnel. You have this massive, complex wave of data coming out of a transformer layer. The first part of the router, the first linear layer, squeezes all that complex data down into a very small essential summary.
A bottleneck.
Exactly. They call this a bottleneck dimension of 128. It just means it's compressing the data down to 128 essential features. Then, it applies a simple mathematical filter called GELU to find the most important nonlinear patterns. Finally, the second linear layer expands that summary back out to make the final skip, execute, or repeat decision.
That is so elegant.
It really is. It's a highly efficient summary desk that barely takes any processing power to run.
That makes so much sense. And the paper notes, they are fully compatible with KV caching. Now, KV caching is something I've heard thrown around a lot. What is it, and why does it matter here?
KV caching is basically the AI's short-term memory during a conversation. Without it, every time the AI generated a new word, it would have to reread your entire prompt from the beginning to remember the context.
Oh, that sounds horribly slow.
It is. So KV caching stores that context.
Yeah.
Because Dr.LLM's tiny routers just integrate smoothly with that short-term memory without disrupting it, it means the whole system stays incredibly fast.
But there is still a massive technical hurdle here that I was wondering about when reading the paper. Say you are an accountant, and you feed a language model a massive financial document, thousands of words long.
Right.
How does this tiny little router, looking through its little 128-feature funnel, make a stable decision about whether to skip a layer when it's looking at this incredibly long, sprawling block of text?
It's a great question. If the router tried to process every single word individually to make a routing decision, it would be completely overwhelmed. The latency would spike. So the researchers implemented a clever trick called windowed mean pooling.
I have a great analogy for this. Think about the last time you had to read a really dense legal contract, like the terms of service for a software update.
Nobody reads those.
Exactly. You don't read every single letter or even every single word to figure out what a paragraph is about. You skim, you take in chunks of text to gauge the general context of the section.
Which is exactly what the routers do.
Right. Instead of agonizing over every token, they average the data, the hidden states of the tokens, into chunks of 8. They're basically looking at the average vibe of those 8 words to decide what to do next.
Skimming is the perfect way to describe it. It compresses the information just enough so the router can make a fast, informed decision without getting bogged down in the microscopic details. But even with that solved, there was another major hurdle in training these routers. And it has to do with the fact that AI models are, mathematically speaking, quite lazy.
The class imbalance problem.
Yes.
Explain this, because it's fascinating. When you look at how the AI operates, over 90% of the time, the absolutely correct action for a layer is simply to execute normally.
Right. And that is a nightmare for standard machine learning.
Yeah.
Imagine you are a student and you realize that your teacher makes the answer true on 90% of the questions on every single test. Are you going to study?
Definitely not. I am just going to blindly guess true for every question, so you know you'll still get an A-.
You take the lazy way out. Exactly. If the right answer is execute 90% of the time, a naive AI training algorithm will just learn to always guess execute. It will completely ignore the rare but vital moments where it should skip or repeat.
So how did the researchers force the AI to study for the test?
They used a technique called focal loss with class rebalancing weights. Sticking with our analogy, focal loss is like the teacher changing the grading rubric so that the few false questions are suddenly worth 100 points each, and the true questions are only worth 1 point.
That changes the math.
Completely. It heavily penalizes the model if it ignores those crucial minority moments where a skip or a repeat is actually the optimal move. It forces the router to pay incredibly close attention to the subtle signals of when it's time to change gears.
Here's where it gets really interesting, because all of this clever engineering, the tiny funnel routers, the windowed mean pooling, the focal loss, the offline MCTS, it translates into some absolutely staggering real-world results. They took this Dr.LLM framework and tested it on some heavy hitters, including Llama 3.2 in both the 3 billion and 8 billion parameter sizes, and Qwen 2.5 in the 3 billion and 7 billion sizes.
And the performance metrics on the in-domain tasks, meaning the logic and math data sets the routers were specifically trained on, are incredibly strong. Across the board, Dr. LLM improved accuracy.
Even on logic.
Yes, on the ARC logic dataset, the gains were modest, an increase of about 0.9 to 2.5%. This makes sense, as logic questions often require more straightforward reasoning where skipping might just trim a little fat.
But the Dart math dataset is where the AI really flexed its new muscles. Accuracy on the math questions surged by up to 4.0%. That is a massive jump, and it comes purely from giving the AI the ability to pause and repeat its own thought process. And while it was getting smarter, it was also getting vastly more efficient.
The layer savings are incredible.
Across the tests, the models save an average of 5 entire layers of computation per example. In some specific cases, they successfully skipped up to 11 layers without degrading the final answer at all.
Saving 5 to 11 layers of complex matrix multiplication for every single prompt a user enters is a monumental reduction in energy use and processing time.
Right.
But if we are being scientifically rigorous, the ultimate test of any AI modification is robustness.
Right.
It's one thing to do well on the exact type of math questions you trained on, but does this routing ability hold up when you ask the AI something totally out of left field?
If I ask it to write a poem or summarize a history book, does the whole thing fall apart? That's the out-of-domain generalization test?
Precisely. They threw a brutal battery of unseen benchmarks at these retrofitted models. Things like MMLU, which tests massive college-level factual knowledge across dozens of subjects. GSM-8K, which is essentially grade school math word problems. You know, if Johnny buys 5 apples and gives the cashier a $20 bill.
Standard reasoning test.
Right. They also use Truthful QA, which tests if the AI falls for adversarial traps and common misconceptions. And Squad DV2, which is strict reading comprehension. These are completely different formats from the training data.
And the results genuinely blew me away. When tested on all those diverse, out-of-domain benchmarks, the models only dropped an average of more 0.85% in accuracy, less than 1%.
Negligible.
All while maintaining their massive efficiency gains. They kept the blazing speed and barely lost a single step in intelligence. In fact, on one incredibly difficult benchmark called GPQA Diamond, which is famously hard even for PhDs to pass using the Llama 3B model, the accuracy actually increased by 2.5%.
That is the holy grail of this kind of architecture research. It proves, without a shadow of a doubt, that the tiny routers didn't just memorize the specific math and logic questions from their 4-hour training session. They actually learned a generalized universal policy for how to efficiently allocate the base model's computational resources, no matter what kind of weird question you throw at it.
And we absolutely have to frame this against the competition. We mentioned other methods earlier. Let's look at one called FlexiDepth. FlexiDepth is a routing method that needs to be trained on a massive dataset of 326,000 examples.
Weird.
And even after all that heavy, expensive training, it loses 6.1% of its accuracy on the GSM-8K math benchmark. Meanwhile, Dr.LLM was trained on just 4,000 examples and hit a stellar 74.9% accuracy on that exact same test. It is doing vastly more with a microscopic fraction of the setup costs.
It really highlights the elegance of their approach, which leads to perhaps the most revealing and honestly most fun part of the paper, opening up the black box to see what patterns these routers actually learned, what is actually happening inside the mind of the AI as it processes a prompt.
This was the major aha moment for me. When they analyzed the router decisions across all the different layers, a beautiful, almost human-like structure emerged. They divided the transformer layers into early, middle, and late stages.
In the early layers, the routers almost exclusively chose to execute. They rarely skipped, and they rarely repeated.
Which makes sense.
If you think about it, it makes perfect architectural sense. The early layers are where the AI is processing the basic vocabulary and structural foundation of your prompt. You cannot skip the foundation. It needs to be perfectly stable before you build on it.
But then you get to the middle layers, and the routers just start handing out skips left and right. The middle is where the fluff and the redundancy live in these giant models. The AI basically realizes, okay, I already have a really good grasp of the context here, so it just fast forwards through the unnecessary repetition to save time.
And finally, the late layers. This is where the routers frequently chose to repeat. The late layers are where the final complex synthesis happens. It is the slow thinking phase. The routers learned that for complex tasks, especially multi-step math problems in the larger 8 billion parameter models, looping those final layers for iterative refinement is the absolute key to getting the right answer.
It is quite literally shifting gears. Fast intuition in the middle, deep scratchpad reflection at the end. But this raises an important question, right? Are they just looking at the surface level text of your prompt and saying, oh, I see the word calculate, this is a math question, I'll repeat the late layers?
This raises an important question indeed. And thankfully, The researchers anticipated it. They designed a brilliant ablation study. Now, an ablation study is an experiment where you selectively remove a piece of a system to see what breaks, isolating exactly what that piece was doing.
Right.
In this case, they trained a new set of routers, but they forced them to look only at the first layer input embeddings.
And for those listening who might not know, input embeddings are basically just the raw mathematical translation of the words you typed in, the surface-level question.
Exactly. They only let the router see that surface-level question type, rather than the ongoing, evolving thought process, the hidden states of the layer right before it.
And the result of that ablation study was a total disaster. Accuracy plummeted by 8.6%.
Which is a fantastic failure, scientifically speaking. It proves definitively that Dr.LLM is not just pattern matching the input text. It is actively reading and reacting to the model's internal state of understanding layer by layer. It dynamically senses how confused or confident the AI is in that exact microsecond of computation, and it routes the data accordingly.
That is just wild to think about. An AI reading its own internal confidence level to decide how hard it needs to think about the next step. And that perfectly sets up one final incredible feature they built into the system. They added a manual dial.
Yes, the scalar control parameter. It's denoted mathematically in the paper as p, which is a value that ranges between -1 and +1.
How does that work in practice for someone using the model?
It allows a user to manually dial the router's behavior up or down post-training, without having to write any new code or retrain a single weight. You can literally just turn a digital knob. If you turn the knob one way, toward the negative, you force the AI to aggressively skip layers. You're basically telling it, I don't care about perfect, deep accuracy right now. I need a fast summary instantly. Or you turn the knob the other way, forcing it to repeat layers for maximum deep thought accuracy.
So you get to define the accuracy versus efficiency trade-off on the fly.
Exactly. It democratizes control over these massive systems. You no longer have to accept a rigid, one-size-fits-all processing speed from the tech giants. You can tune the AI's cognitive load to match the specific needs of your application right in that moment.
So what does this all mean? Why should you, as the listener, care about this deep dive into layer routing and Monte Carlo tree searches?
Well, it's not just theoretical math meant for supercomputers in a sealed lab. This breakthrough means that the incredible AI applications we all rely on every day could very soon run much faster and much cheaper. We are talking about massive, incredibly smart LLMs that could eventually run directly natively on your laptop or even locally on your phone without instantly draining your battery.
By acting more like a human brain, seamlessly shifting gears from quick, effortless intuition to slow, deep reflection, these models become practical, sustainable tools for everyday, low-power devices.
It is a critical step forward. We are moving away from the era of brute force computation, where we just throw more electricity at a problem, and moving toward an era of elegant, budget-aware reasoning.
And that leaves me with one final kind of mind-expanding thought for you to mull over. We just learned that an AI can be retrofitted with tiny little routers that read its own internal state of understanding to skip or repeat its logic paths.
Right.
If an AI can sense when it is confused and realize it needs to think twice about a tricky math problem, could this exact same architecture eventually be used to route an AI away from moments of hallucination? Could it soon learn to sense its own internal uncertainty and realize it needs to think twice before making a flawed moral or factual judgment? That is a wild frontier.
A truly fascinating possibility to consider as we watch this technology evolve.
Well, you have a lot to think about. Thank you so much for joining us on this deep dive into the dynamic mind of Dr. LLM. We will see you next time.
Thank you for listening.